All right, let's talk about 1.6 absolute value functions. So, our first definition here concerns the absolute value function itself. So the absolute value function is best defined as a piecewise function. F of x is the absolute value of x, that's how you read this with the bars around it. And that is exactly the piecewise function, x if your x was greater than or equal to 0, and negative x otherwise, if it was less than 0. Notice that when we say x is greater than 0, what we really mean is just positive or 0. So this thing takes in an input, and it says, well, if it was positive, basically leave it alone. Otherwise, if it was negative, toss a negative in front of it. That is, if it was negative, that's what that means. So this is if it's positive, this is if it's negative. It's just going to toss a negative in front of it. And obviously a negative makes a positive. The important thing to get out of this is that the function absolute value of x will tell you the distance the number is from 0 on the number line. So, to understand this a little bit better, let's look at an example down here. So, it says, determine all values x within a distance of 5 from the number 3, including the distance of 5 itself. So, we're going to use the absolute value function to do that. So, we need the distance between x and 3 to be less than or equal to 5. So let's take a look at this on a number line real quick. Here's the sort of situation that we're looking at. So here's a number line. Let's use this real quick. And the number that we want to talk about is 3. So let's put 3 on the number line. And then we want to know all the numbers a distance 5 away. So we're going to go up 5 to get here. We're going to go down 5 to get here. So 3 plus 5 is 8. 3 minus 5 is negative 2. And what we want to know is, well, this distance here. We're a distance 5. That is this distance here from right here all the way over. And also this distance. Well, they're both 5. This situation right here is going to be written as x minus your number that we've moved. So 3 and absolute value less than or equal to 5. And this is how you're going to go ahead and write this. So what this says is this is everything that is a distance 5 from the number 3. This will be very useful later on in calculus. So let's take a look at another example right here. So this example asks us to determine all values x within a distance of 2 from the number 1. So let's take a look at this. We want all values x within a distance of 2 from the number 1. So think about this on a number line real quick. So this is the number 1, and then we're going to go over 2, so up to 3, and we're going to go down 2 to negative 1. This distance in between here is 2. This distance in between here is 2. The way that you're going to write this is the absolute value of x minus something, all right, is less than something else. Now, what goes where is the question. Well, we are a distance here, goes here, and the number that we are orbiting around, if you can think about it, we're orbiting around 1, actually goes inside of the absolute value sign. It is very good to think about this as a distance, and it makes sense that coming from here at 1 back to negative 1 is still a distance of 2. Think about this. If you were standing on this number line and you had to walk all the way over to the left, to get to negative 1, you still walked 2 miles. You didn't somehow walk negative 2 miles and regenerate your stamina somehow. You still had to expend effort to get there, and that is what absolute value is often used for in mathematics, talking about strictly positive quantities. So This is how you determine all values within a distance of 2 from the number 1. Another way to think about this is that this is actually saying two different things. So at the same time, this is saying two different things, and we'll look at both of them. This is saying that x minus 1, not an absolute value, is greater than 2, like this. And it's also saying that x minus 1 is less than 2. And when I say 2, I mean negative 2. So we have x minus 1 bigger than negative 2, but x minus 1 is also less than 2. And if you solve each one of these, you will see pretty clearly exactly what it is that we're talking about. So we add 1 to both sides, and we get negative 1 less than x. And we add 1 to both sides over here, and we get that x is less than 3. So we're going to be between 3 and negative 1. You can even write both of these things together, and I'll do it in a nice orange here. You can write both of these things together as the compound inequality, negative 1 less than x less than 3. Now, we said that this is within a distance of 2 from the number 1. Notice how there is no equal to here. Okay? But if we scroll back up to the previous example, you'll notice that there was an equal to. So why was there an equals to here? Well, we said it. We said including the distance of 5 itself. So that's the main difference between these two. This thing right here is called a compound inequality, in case that ever comes up. And this is how you deal with these sorts of things. In fact, we can even scroll back up here, and we can rewrite this as a compound inequality as well, just for a little bit of extra practice if you want to. You say that x minus 3, and then you take this symbol, put it on the left for this one, make it negative, and over here you write it again, except without the absolute value signs. If you solve both of these by adding 3 to both sides, adding 3 to negative 5 will give you this negative 2. Adding 3 to this 5 will give you the 8, and the overall compound inequality is negative 5 less than or equal to x minus 3 less than or equal to positive 5. And you can think of solving this a different way as just adding 3 to each one of these parts. Add 3 to negative 5, you get negative 2. Add 3 to x minus 3, you get x. Add 3 to 5, you get 8. So that's another way to solve these sort of things. But everything that this number line is saying is said here, is also said here, is also said in this compound inequality. So it's however you want to look at it. But you'll notice that this is a very compact way to say all of the rest of this information. So let's continue. So now we want to graph the absolute value function. So we want to graph both f of x equals x plus 4 and g of x equals the absolute value of x plus 4 on the same graph, and then see what we can learn about it. So let's go ahead and draw ourselves a coordinate plane here. And we're going to do f of x in this orange, and we're going to do g of x in this cyan. So let's start with the orange one. Let's graph f of x equals x plus 4. Well, this is a line with a slope of 1 over 1 and a y-intercept at 4. So we can come up here to 4. Okay. And we can go ahead and try our best to graph this line. So it has a roughly diagonal slope like this. And if we keep it roughly straight, it looks something like this. So think about what the g of x is going to do. What's the difference? The only difference between these two things, between this 1x, which I should probably write like this, between this 1x plus 4 and this absolute value is obviously the absolute value sign. So what is ultimately going to get changed? Well, as long as your output is positive from the definition, as long as your output is positive, nothing is going to change. It's exactly the same thing. As long as what you are putting in, your overall input here, the x plus 4 part, is positive, it's going to look exactly the same. So from here at this x-intercept, all the way up, it is going to be positive. And by the way, if we wanted to figure out exactly what this x-intercept was, it would be pretty easy to do that. We would just take x plus 4 and set it equal to 0, and obviously we would get negative 4 out, so I can go ahead and put that on there. But now think about the input here, x plus 4, with the absolute value. The output can never be negative. So what's going to happen is instead of it going down into this third quadrant where everything is negative, we're going to see it come back up like this. And the absolute value of x plus 4 is going to look exactly like this plus this part over here, which I'm going to lightly shade over. The whole thing, this whole v. And in fact, all absolute value functions look like v's. And of course, if you remember back to what we talked about in the last section, you'll know that we're adding 4 into the input of the function. So the absolute value of x just looks like this green one here. It's just going to look like this. It's going to be this v guy here going off forever from 0, 0. And of course, adding 4, we added on the inside, so that's going to shift us left. How many units? 4 units. And you're going to get this whole v situation here. That's the absolute value function. So these things can get a little bit more complicated, but the main takeaway is that all that this is, and I'll take some of this data off here, all that this is it's just your normal line, except all the negative parts, you can think of it as bounces off the x-axis and stays positive. Now, is it ever possible for parts of this absolute value function to actually be contained in quadrants 3 or 4? You can take a moment to think about it, but we're going to move on to the next example and look at that. So in this example, we're asked to graph the function f of x equals 2 times the absolute value of x minus 4 plus 3. And of course, this is all just from 1.5, and we can identify some of the key stuff here. So let's start with this nice orange. This is your a. So your a is 2. So let's go over all this. Our a is 2. Let's keep track of this over here. It's always good in mathematics to write down what you know. Your b is 1 because there's nothing in front of the x here. There's nothing in front of the input. Your c is 4 because the standard form has the minus attached to it. And your d is 3. And then let's translate what all of that means, and we'll do that in a angry red. So this is a vertical stretch by 2. So it's a vertical stretch by 2. Nothing happens with b because it's just positive 1. C is 4. So this negative 4 is going to move it to the right by 4. So right 4. And then D is 3. So we're going to go up 3. Okay. So it's useful to take a look at this and see exactly what happens as we move it around. So let's go ahead and draw ourselves a coordinate system here. And we're going to need to label some numbers. So let me get some numbers on here. And we can take a look at it. So I've only labeled 1 through 5 on the vertical y-axis and 1 through 5 on the vertical x-axis, which I can go ahead and label as well. It's always a good idea to label your axes. Because I know that we're going to be vertically stretching and we're going to be moving to the right and up, so I know I'm not going to need the left and down. So let's just graph right now what f of x equals. Let's graph another function. Let's graph g of x. Let's graph g of x equals the absolute value of x, just so that I can show you the difference. So it has a slope of 1 over 1, and roughly looks like this. And it's very much worth it to remember this. So all we're going to do is take this function and transform it according to these rules. So we're going to move its center point from at the origin to somewhere else. So let's do it in red. We're going to move the center point right 4 and up 3. So we're going to move it right 4 and up 3 to about right here. And then we're going to do a vertical stretch of 2, which has the effect of making the slope, instead of 1 over 1, 2 over 1. Right now the slope is up 1 over 1, up 1 over 1, up 1 over 1. This changes it to up 2 over 1, up 2 over 1. So from here, we're going to go up 2 and over 1 and plot another little point. And then we're going to go up 2 and over 1 in the other direction because we know that it's still going to be a V shape. And maybe I can get that a little bit more on. There we go. And then we're just going to draw the V through it. And I know that that's everything. So that is a graph, in red, is the graph of f of x. 2 times the absolute value of x minus 4 plus 3. It's been moved to the right 4, because this was negative. It's been moved up 3, and it has been stretched by a factor of 2. That is, its slope has been changed. And that is a way to think about this. Graphing these by hand is a huge part of the class, being able to graph any kind of function by hands. But overall, it's worth it to remember the shapes of the graph. So absolute value of x is something you should absolutely be able to draw by memory, no pun intended. And it is just a V shape with a slope of 1 over 1 on both parts, bouncing off at the origin and continuing into quadrant 2 over here. So this example says that an absolute value function is sketched below. Tell its equation. So it's exactly the flip of what we previously dealt with. And this is a very rudimentary sketch. Obviously, a better problem would be showing you the graph via Desmos or whatnot, but that kind of gives it away a little bit too much. Let's look at this. This thing looks like it has roughly a slope of 1 over 1, so we can take a bunch of guesses as to what's been done here. So it's neither been vertically stretched, nor compressed, nor horizontally compressed, nor horizontally stretched, because it has a slope of 1 over 1, though it is flipped, obviously. It's down here in this quadrant. And you may say, well, absolute value functions can never evaluate to a negative number, and that is correct. However, once you've transformed one of these, what you've done is, well, we'll see here in a second. So obviously, normally, our vertex would be right here at 0, 0 in the normal function. So how have we moved this? We have moved it to the right 4 and down 2. So I know that our function is going to end up looking like the absolute value of something times x plus or minus something. I'll write minus. Okay, and then plus d, and then there's an a out here as well. So this is your f of x, and I know that something goes right here for a, right here for b, right here for c, and right here for d. So we just need to fill in the blanks now. So we know that this equals, and now we just need to fill in all the blanks. Well, it's usually easiest to fill in the translations first. We have moved it to the right 4 and down 2, which means that we are going to have to say, well, we've moved it down 2, so we can subtract 2 or add negative 2. And we have moved it to the right 4, so you subtract 4. You subtract to move right, you add to move left on the inside of the function. What I mean by the inside of the function is inside of whatever the function's doing. So inside of the absolute value in this case. Now, we said that we have neither stretched nor compressed it in any direction, and I can tell that by looking at it. And you could too if everything were labeled. So we know that each of these are 1. The question becomes, well, we flipped it. How do we flip over the line y equals negative 2? How do we flip vertically? It was supposed to be like this, a normal v, and now it's an upside down v. How did we flip? Well, we flipped vertically. Vertical things only happen on the outside of your function. And this has nothing to do with flipping anything, so this must be negative. Meaning that your overall function must look like, writing this a little more simply, the negative, the absolute value of x minus 4 minus 2. This is your answer. You have flipped it over the line y equals negative 2. You have moved it to the right 4 and down 2. And you can see all that just by looking at this. Several of these show up in your work, and you're asked to do a bunch of this. And this kind of analysis of the mathematics is precisely what gives math analysis its name. You are analyzing what's happening to the function. It's literally where the name of the course comes from. So it's worth knowing. So now we're going to move on to another topic called absolute value equations. And it is as simple as it sounds. It's just solving equations or inequalities involving absolute value. And it's super easy to show you how to solve these sorts of things because they basically just break down into two cases. Let me show you this first one. The absolute value of 2x plus 1 equaling 3 is going to break down into two cases. It's either going to break down into this case over here or this case over here on the right. One case is that 2x plus 1 equals 3. The other case is, well, what if it was negative? Because remember, what the absolute value does is it says, well, it's either going to be the inside was x, was whatever was plugged in, or the inside was going to be negative, whatever was plugged in. Now, most of you all that have been taught this before weren't taught it this way. You were taught, well, just divide both sides by -1 to start with, and you actually started it with this. Equals -3 like this. You would have just written this part here and this part with a negative over here. What you're actually doing is this first part. You're welcome to start with just this though. So it either equals positive whatever was over here or the negative of whatever was over here. But either way, you just solve both of these equations and both answers are simultaneously answers. So we're going to subtract 1 and divide by 2. And we're going to get that x equals 3 minus 1 is 2, divided by 2 is 1. That's one of your answers. Your other answer is subtract 1 to get -4, and then divide by 2 and get -2. So your two answers are x equals -1 and x equals -2. And if you wanted to check them, you could just plug them back in and see that it does indeed work. 2 times -2 is -4, plus 1 is -3, and the absolute value of -3 is 3. And if you plug in 1, 2 times 1 is 2, plus 1 is 3. The absolute value of 3 is 3. Both of them work. That's all there is to this. Let's move on and do another one. This is an inequality, and we need to solve the absolute value of -x plus 4 is less than 6. Here's how you solve it. Write it down. -x plus 4 is strictly less than 6, and that's going to break down into two cases. Either -x plus 4 is in fact less than 6, or we have that -x plus 4 is less than 6. All right? The reason that I taught this to you different than you've been taught it before is because when there's inequalities, it matters. Because when we multiply both sides by the -1 or divide both sides by the -1, remember, you have to change the sign. So it's going to be greater than -6, because we multiplied both sides by this negative to get rid of it. This is why I prefer writing the actual argument of the absolute value function itself as either itself, for one case, copy the rest, or negative, in parentheses, itself, for the other case, because you can always use the same sign both times and then just remember to flip it when you actually do a little bit of extra math. If you want to remember that you just, to do an inequality, you make the other side negative and flip the sign, that's fine. But I would rather you know where this is actually coming from. From here, obviously, this is pretty easy to solve. So we're going to subtract 4 from both sides and get that -x is less than 2. And then we're going to multiply both sides by -1 and get that x is greater than -2. Remember, you have to flip the sign when you multiply by a negative or divide. We're going to subtract 6 from both sides and get that -x is greater than -10. And then we'll finally get that x is less than 10. So x needs to be greater than -2 and less than 10. That's cool, you've answered it. Now, what if I asked you to write this as a compound inequality? You would notice that this is exactly the same thing as -2 is less than x, and if x is less than 10, you could rewrite the whole thing as a compound inequality as -2 is less than x is less than 10. And another way to read this is x is between -2 and 10 exclusive, meaning you're not including the inbound. If both of these were equal to, so -2 is less than or equal to x is less than or equal to 10, that you would say inclusive. X is between -2 and 10. Inclusive means including the bounds. Exclusive otherwise. If you wanted to write this in interval notation, it would be -2 to 10, as opposed to with brackets to include the bounds. Easy enough. Let's look at another one. So this one looks different. The absolute value of 4x plus 1 greater than or equal to 3. All right, nothing to it. I submit. Let's go ahead and write this. 4x plus 1 greater than or equal to 3. It's going to break down into two cases. I'm not even going to bother drawing the arrows this time. It's either 4x plus 1 is, in fact, greater than or equal to 3, like we think, or negative 4x plus 1 is greater than or equal to 3. And then remember, when you come from the first step to the second step in this, you just flip the sign, because you multiplied both sides by a negative 1. That way you don't have to remember an extra rule. You can just use rules that you've already used. And now we're just going to solve each part of this. We're going to subtract 1 and divide by 4, and there's no negatives in here for us to deal with. So subtracting 1 gives us 2, dividing by 4 gives us 2 over 4, or 1/2. So x is greater than or equal to 1/2. And then over here we're going to subtract 1, which gives us negative 4, and divide by 4, so we'll get negative 1. So x is less than or equal to, again, this was minus 1 is negative 4, divided by 4 is negative 1 overall. All right, so our x is greater than or equal to 1/2, and less than or equal to 1. You may notice that you couldn't actually write this as a compound inequality if you wanted to, because we're saying everything bigger than negative 1/2 and everything less than or equal to 1. That is, using interval notation, we're saying everything bigger than or equal to 1/2, so let me use the right symbol, bigger than or equal to 1/2 is this. And we're also saying less than or equal to negative 1. So less than or equal to negative 1 looks like this. And we're sticking them together. This is what this looks like. There's no way to write this as a compound inequality. That is, on a number line, and I know this is probably overkill, but on a number line, here's negative 1, and here's 1/2. What we're doing is we're including these points, and then shading in all of this, and then we're including a number line and shading in all of this. And remember that a compound inequality like this says in between. So this situation over here is exactly this. If you want to look at it this way, it's here's negative 2, here's 10. That is, we're not including these, so we'll put circles, and then it's everything in between here. That's that situation on a number line. Between actually is just a single interval. This you're not able to write like this in example 8 here. So you can't write this as a compound inequality. So if I said write it as a compound inequality, you just say, nah, I can't do that, boss. Sorry. All right. Let's do a couple more examples, and then we'll be done. So example 9 here says, solve this. And it says careful here. And that's a reminder to look at this very carefully before you try to solve this. So first thing you may try to do is say, okay, well, let's just blindly follow the math and see where it leads us. So 3x plus 2 greater than or equal to negative 3. All right. So I'm going to cut this in half, and I'm going to say, well, then 3x plus 2 has to be greater than or equal to negative 3, or negative 3x plus 2 is greater than or equal to negative 3. And then I do the math here, and I get that 3x plus 2 then has to be less than or equal to 3. And then I just solve this down. So I add 2 to both sides and then divide by 3. So subtract 2, rather. So I'm going to subtract 2 and get negative 5 over 3 for this. So negative 5 over 3. And then I'm going to do the same thing. I'm going to subtract 2 and get 1, so I'll get 1/3. Less than or equal to 1/3. And then we're going to look at this really. So we need a number that is both less than 1/3 and also greater than or equal to negative 5/3. So you may do some math here and say, okay, well, negative 5/3 less than or equal to x, less than 1/3. So you could write this as the compound inequality, negative 5/3 less than or equal to x, less than or equal to 1/3. So any number in between these two would satisfy it, you say. Right? I mean, you did the math, right? So that must work out, but think a second. I said be careful here, and I'm not always going to say that. We're not adding or multiplying by anything on the outside. Your a and your d are both 1 and 0, respectively. So this is strictly an absolute value. And remember, the very definition of absolute value is the absolute value of a number is always positive. It's always positive. So, what did we find? What does this even mean? Does this mean anything? Take some of the numbers here and plug them in. Let's pick a number, a very easy number, and see what we actually found here. What did we actually find? Let's take this negative 5/3, for example, and let's plug it in. Negative 5/3, we're going to take it and plug it in and look at it real closely. So negative 5/3 is the number that we plugged in. So we take the number we plug in, we multiply it by 3, we add 2, and then we take the absolute value of all of that. So like this, and we're saying, is this greater than or equal to negative 3? Well, obviously, when you cancel that, because that's how that works, negative 5 plus 2 is negative 3. Absolute value of 3, of negative 3 is 3, which is, in fact, greater than or equal to negative 3. So that is going to give a meaningful answer. But this is a strange thing to think about. Now, let's take a look real quickly at this entire problem if I zip all the way back and change one little thing about this whole thing. Let's instead reverse this and make it less than or equal to. Okay? This is a meaningful problem because it being greater than a negative number is something that it can do. But let's say that we want it to be less than or equal to negative 3. Or, even more likely, let's solve another version over here as well. Again, a completely different problem. The absolute value of 3x plus 2 equals negative 3. Okay, let's look at both of these problems. This problem is solvable and has some meaning, though it's a strange thing to ask because, of course, this is going to be greater than or equal to 0, in fact, not just negative 3. But let's take a look at this here. It doesn't matter what 3x plus 2 evaluates to. Think of this boy in this box here as one big unit. This is just going to evaluate to some number. No matter what that number is, we're going to take the absolute value of it. So if it's a positive number, we're going to get out a positive number. And obviously, you can't have a positive number be be less than or equal to a negative number. And if it's a negative number in here, we're going to take the absolute value, and the whole thing's going to be positive. And obviously, a positive number is not less than or equal to a negative number. It's greater than or equal to. It's the exact same thing over here. Whatever this 3x plus 2 evaluates to, we're going to take the absolute value of it, and it's going to be positive. A positive number can't ever equal a negative number, much less negative 3. So these two cases, in both cases, you just say it doesn't exist. There is no x that satisfies either of these equations. And it's arguable. There are some x's that satisfy this one, but this isn't even a very well-formed question to begin with. I mean, it makes some sense. If you go graph this thing in Desmos, you can see what it is we're talking about exactly. But this last part here is, well, it's got some redundant extra stuff in here that we don't need. Negative 3, this may as well have been a 0, and we'd have got the same information out. All right, so let's look at the last example here. It says to find the zeros of this function, f of x equals 3x minus 5 minus 3. In order to find the zeros of any function f of x, this one in particular and all other ones, you take the function, you set it equal to 0, and you solve that bad boy. So in order to do this, all that we're going to do is take 3x minus 5 equals, 3x minus 5 rather, minus 3. We're going to set it equal to 0, and we're going to solve it. Because the zeros are where this function evaluates to 0. That is, it's on the x-axis. The zeros are the x-intercepts. It means the exact same thing. And it's worth it to remember that for when we get to polynomials. So this is the x-intercept. All right? So let's go ahead and solve this. So in order to solve these, it's pretty easy. You just add 3 to both sides. So you get the absolute value of 3x minus 5 You add 3 to both sides. So get rid of your a and your d first. There was nothing over here for us to get rid of, so we're going to get rid of our d as well. And now you just solve this like the equations that we solved back up. This breaks down into 2 cases. What are the 2 cases? The cases are 3x minus 5 equals 3, and the cases are negative 3x minus 5 equals 3. And then we solve from here. So we add 5 and divide by 3, and we get 8/3. Please don't convert that to a decimal. And then here we slide our negative over first, equals negative 3. And then we add 5 and divide by 3, and we get that x equals 2/3. So those are our 2 options. So our 2 x-intercepts. The x-intercepts, if I asked you to find, by the way, the x-intercepts, if I said find the x-intercepts of this, they're not 2/3 and 8/3. Those are the zeros. Intercepts are points. So the 2 x-intercepts would be the points 8/3, and we made you get 0 for the y. This literally says y equals 0. And also 2/3, comma, 0. These are the x-intercepts, if I asked you for those. Intercepts are points. Intercepts are points. Zeros are just values. If you want to write these 2 things one last way, of course, you can write it as a solution set, which is a set containing the solution. In no particular order, but ascending order is nice. Just on your teacher. All right. So these are all the different things that you need to learn from this chapter. So now you're ready to go do all the work.